And our last speaker is Professor Takuro Mochizuki of Kyoto University. Professor Takuro Mochizuki is a recipient of the Frontiers of Science Award. He will talk about mixed twistor D modules and generalized Hodge theory. Please welcome.
Well, thank you. It's my great pleasure to give a talk in the International Congress of Basic Science of this year. And I'm also very glad to visit this wonderful institute, BIMSA. And so I thank the organizers and the committee members for selecting this work and for the invitation. And it is extremely encouraging to me. So in this talk, we shall discuss mixed twistor D modules. So the interaction between algebraic geometry and differential geometry has led to many important progress in mathematics. For example, one of the most classical is the theory of compact Riemann surfaces. A compact Riemann surface is defined to be a compact connected to one-dimensional complex manifold. And it is also expressed as smooth connected complex projective curve in a very algebraic way. And both algebraic and analytic methods are useful in the study of Riemann surfaces. And it is very interesting to study a good differential geometric structures of algebraic objects. For example, a good differential geometric structure of a Riemann surface is a conformametric with constant curvature. And there is an equivalence between complex smooth projective curves and compact oriented surfaces with constant curvature. And it has been generalized to the very deep and intensive study of Kähler-Einstein metrics and more generally constant scalar curvature Kähler metrics. And let me mention another typical example. A good differential geometric structure of an algebraic vector boundary on a Riemann surface is a flat Hermitian metric. I mean, a Hermitian metric of an algebraic vector boundary induces a unitary connection called the Chern connection. And the condition is the vanishing of the curvature of the Chern connection. And on the side of algebraic geometry, there is the stability condition. An algebraic vector boundary on a compact Riemann surface is called stable if the slope of any non-trivial algebraic subboundary is strictly smaller than the slope of the boundary. The slope means the ratio of degree and the rank of. And then, according to the famous theorem of Narasimhan and Seshadri, algebraic vector boundary on a compact Riemann surface is stable of degree 0 if and only if it has a flat metric such that the induced monodromy representation is irreducible. And this theorem was generalized to the study of so-called Weistinci correspondence or Donaldson-Winnicott correspondence for stable vector boundaries and Hermitian-Einstein metrics. And it was also generalized to the non-abelian Hodge correspondences for Higgs boundaries and flat boundaries and harmonic boundaries in the higher dimensional case and the singular case. And when we consider such a kind of good differential geometric structures, one of the naive hope is to obtain an equivalence between objects in algebraic geometry and objects in differential geometry. I have already mentioned typical examples. And the benefit of this kind of equivalence go both ways. Very roughly speaking, objects in algebraic geometry are defined by algebraic equations, and objects in differential geometry are defined by differential equations. And in principle, solving differential equation is more difficult than solving algebraic equations. And moreover, in algebraic geometry, many strong and powerful methods and techniques have been developed with rigorous foundations. So even if it is very difficult to find just one example on the side of differential geometry, it must be possible to construct many examples or to classify all the objects on the side of algebraic geometry. And conversely, differential equations might have more useful information compared with algebraic equations. So it might be helpful to understand the objects more deeply. Actually, for example, it is very useful in the study of the moduli spaces. So it is very nice to have this kind of equivalence. And another or second naive hope is to enhance algebraic operations by good differential geometric structures. In algebraic geometry, there are many useful functors which could, to create an object from another. And it is one of the advantages of algebraic geometry. And it is it is very nice if we can enhance such functors by differential geometric structures. For example, when we are given a morphism of compact Riemann surfaces from X to Y, then an algebraic vector bundle on Y induces an algebraic vector bundle on X by the pullback. So this is purely algebraic operations. And the flat metric of the bundle on Y induces a flat metric of the pullback of the bundle on X. So the pullback of algebraic vector bundles is enhanced to the pullback of unitary flat bundles. And let me remark, this implies the pullback of a stable vector bundle of degree 0 is a direct sum of stable vector bundles of degree 0. And this is a statement purely in algebraic geometry, but it is not easy to prove it purely in algebraic geometry. So the enhancement of algebraic operation by good differential geometric structure should have some non-trivial consequence. And let me also remark, we cannot expect such functoriality for usual good differential geometric structures. For example, we consider a morphism of projective manifold equipped with Taylor matrix. Then the pullback of from X to Y, then the pullback of a harmonic function on Y is not necessarily a harmonic function on X. So if we consider a differential geometric structure defined by elliptic nonlinear partial differential equation, then we can't expect, usually we can't expect the pullback without such structures. So the enhancement of algebraic operation by good differential geometric structure can happen only in very special cases, very good cases. And let me mention another good example, that is the Hodge structure of a smooth projective manifold. The Durham cohomology group of smooth projective manifold can be considered as the hypercohomology group of the algebraic Durham complex. So we can regard it as a purely algebraic object. And the harmonic theory gives the Hodge decomposition of the Durham cohomology group. So we can regard it as an enhancement of the cohomology group by Hodge structure, which is a kind of good differential geometric structure. So in this talk, we'd like to explain a good differential geometric structure of algebraic harmonic D modules is given in terms of a twistor structure, that is a generalization of Hodge structure. And in this case, both naive hope 1 and naive hope 2 are achieved. And I'd like to also mention, from the viewpoint of twistor structure, Hodge theory could have a much broader scope. I mean, there should be much more equivalence of objects and enhancement of functors, which have been thought to be less related with Hodge theory. So in the following my talk, first we record holonomic D modules. And then I'd like to explain twistor structures and mixed twistor D modules. And then I'd like to mention an attempt toward a generalization of an aspect of Hodge theory. So let me begin with harmonic modules. Actually, it was already explained in the excellent talks by Professor Daniel and Professor Live in the last week, but let me repeat it. So let X denote a complex manifold, and let Dx denote the sheaf of holomorphic linear differential operators on X. It is a sheaf of algebras, and if X is an open subset of Cn, then we can describe it as in this way. And in this talk, a sheaf of left modules over dx is called a dx module. Sometimes it is more convenient to consider right dx modules, but in this talk we consider only left dx modules. Let me show you some easy examples. The sheaf dx itself is naturally a dx module. And another typical example is the sheaf of holomorphic functions denoted by OX. And in general, a dx module is equivalent to an OX module equipped with an integrable connection, which is a linear morphism from E to E test omega x1, satisfying the Leibniz rule and the integrability conditions. And if the underlying O module is locally free, then the D module is also called a flat bundle. For example, for any holomorphic function G, we can consider the integrable connection D plus dg of the structure sheaf. So we have the corresponding D module. And let Fj dx denote the subsheaf of differential operators of order at most j, given in this way. Then the product of Fj dx and Fk dx is contained in Fj plus k dx. So we can consider the associated graded sheaf of algebras, and it is isomorphic to the symmetric tensor product of the tangent sheaf. Theta x denotes the tangent sheaf of x. And a good filtration of a coherent D module is an increasing and exhaustive filtration by coherent OX submodules, such that the product of Fj dx and Fkm are contained in Fj plus Km, and satisfying some finiteness condition, that is, the least module of M is coherent over the least module of dx, this algebra of dx. Then, from such a good filtration, by considering the associated graded object, we obtain a coherent sheaf on the cotangent bundle of X. I mean, the associated graded sheaf graded algebra of dx is atomic the symmetric tensor product to tangent sheaf, so we can obtain a coherent sheaf on the cotangent bundle of X. And the support of the coherent sheaf is called the characteristic variety of the D module. And according to the theorem of Sato and Kashibara and Kawai, which was later proved by Gaba in much simpler way, but anyway, according to their theorem, the characteristic variety of a D module is always coisotropic with respect to the natural symplectic structure of the cotangent bundle. So in particular, the dimension of the characteristic variety is always larger than the dimension of X. Then, so we say a D module is harmonic if the dimension of the characteristic variety equals the dimension of X. So this is one of the main objects in this talk. In a previous example, dx is not harmonic if the dimension of X is positive. The characteristic variety of dx is equal to the cotangent bundle of X. So if the dimension of X is positive, dx cannot be harmonic. And the characteristic variety of OX is the zero section in the cotangent bundle. So OX is always harmonic. And more generally, any flat bundle is harmonic. So in particular, the D module given by OX into D plus DG is harmonic. And for any linear ordinary differential equation, we can consider the corresponding D module. And it is easy to see this D module is harmonic. And actually, many of the important properties of ordinary differential equations can be generalized to the context of harmonic D modules. For example, sections are always finite dimensional. So in this sense, we can regard harmonic D modules as appropriate higher dimensional generalization of linear ordinary differential equations. And there are many useful functors on the category of algebraic harmonic D modules. And it is one of the reasons why D modules are useful in mathematics. So, so we call the derived category. And for any algebraic morphism of complex algebraic manifolds, we have two types of direct image functors and two types of inverse image functors. And I don't explain the precise definition of these functors. But for example, if x is a product of y and z, and f is a projection to y, and suppose d is compact, then the two direct image functors are the same, and it is given by the push forward of the relative drum complex of the D module. And if y is a point, y consists of just one point, then the push forward of the structure shift is the drum cohomology or drum cohomology with compact support up to shift of the degree. And there are also other useful functors like tensor product and inner homomorphism and duality and the nearby cycle functor and the vanishing cycle functors. And we would like to enhance these standard functors by twistor structures. But before twistor structure, let me explain R modules. So let P lambda denotes the projection of C lambda times X onto X. And let theta X denote the tangent sheaf of X. And let Rx denote the sheaf of subalgebras in the sheaf of differential operators generated by lambda times the pullback of theta X, pullback of the tangent sheaf. So it is by definition sheaf of algebras. And as in the case of D modules, in this talk, a sheaf of left modules over Rx is called an Rx module. If X is an open subset of Cn, then by setting del P as lambda times del P, we can describe Rx in this way. And we have the commutation relation between del P and the coordinate function GQ, like this one. So the name of R module is not standard, but R modules are very common objects in many fields of mathematics, in particular studying quantization. And the restriction of Rx, for any non-zero lambda, the restriction of Rx to lambda times X is isomorphic to dx. And the restriction of Rx to 0 times X is isomorphic to the symmetric tensor product of the tangent sheaf. So outside of lambda equals 0, Rx modules have the properties of D modules. And at lambda equals 0, R modules have the properties of Forty-star X modules. And we'd like to relate or combine these properties. And one of the important conditions is the strictness. We say an R module is strict if it is flat over OC lambda. And this condition is important in relating or combining the properties of D modules and OT-star X modules. And as in the case of D modules, we also consider holonomicity condition. I mean, for any coherent Rx module, we can consider the characteristic variety, which is defined as a subvariety of the product of C and the cotangent bundle. And we say an R module is holonomic if there exists a Lagrangian cone in the cotangent bundle of X, such that the characteristic variety of the R module is contained in the product of C and the Lagrangian cone. the simplest example of stochastic harmonic R module is the structure C of C times X. And in the case of D module, in general, an Rx module is equivalent to an OC times X module equipped with a family of integrable connections in the X direction, which is meromorphic of order 1 along lambda equals 0. This is meromorphic of order 1 along lambda equals 0. So, for example, for any holomorphic function g on x, we can consider the family of meromorphic family of integral connections given by dx plus lambda inverse dg. So this gives a Rx module, and it is strict and harmonic. And another important source of examples are given by harmonic bundles. Let E theta be a Higgs bundle on a complex manifold X, which means E is a holomorphic vector bundle, and theta denotes end-invalid holomorphic one form satisfying theta square equals 0. And when we are given a Hermitian metric of the bundle, we obtain the Chern connection and the adjoint of the Higgs field with respect to the metric. So we obtain the connection as obtained as the sum of the Chern connection and the Higgs field and its adjoint. And if this connection is integrable, then the Higgs bundle with the metric is called a harmonic bundle. And harmonic bundle induces strict harmonic Rx modules. I mean, the pullback of the bundle to C lambda times X is equipped with the holomorphic structure twisted by lambda theta lambda H. And it is also equipped with the meromorphic family of integrable connections given in this way. So this gives this gives an harmonic this gives an Rx module, and it is strict and harmonic. So this is a very important example for us. And most functors for D modules have something similar in the context of R modules. But strict harmonic R modules do not behave well with respect to the functors. For example, we can consider an analog of Drum complex for R modules. I mean, we can obtain the complex of sheaves on C lambda times X as an analog of, and in the case of D modules. And and in this case, by taking the direct image of this complex by the projection of C times X to C, we obtain the analog of Drum cohomology groups. And in this case, these guys are all C lambda modules. And even if the original R module is strict and harmonic, these guys are not necessarily strict. I mean, in this case, these guys are not necessarily locally free O modules. So the strictness is not preserved by the direct image for R modules. And let me remark, this strictness is related with very interesting issue in algebraic geometry. For a meromorphic function G on Xh, we can consider the twisted drum complex. This is the shape of the exterior forms, and this is given the derivative differential is given by dx plus lambda inverse dg. And it is interesting to study the strictness of the direct image of this complex by the projection of x times c to c under appropriate boundary conditions. The most famous result is a theorem of Green. So we consider the case G equals 0, antitwisted case, and suppose X is projective and H is normal crossing. Then the spectral sequence associated with the filtered logarithmic drum complex degenerates at the E1 stage. And this is equivalent to the strictness of this direct image, the direct image of this kind. And this is very deep theorem based on Hodge theorem. And another famous result is a theorem of Baranikov and Kontsevich. they consider the case G induces a projective morphism from X to P1, and H is strictly the pole of G. In this case, they proved the strictness of this direct image. And there are many variations of these results. And they are interesting, for example, they are useful for example, for the computation of the dimension of the cohomology groups. And it is also useful to obtain some vanishing theorems. And it is also useful because it is related with the study of the Landau-Ginzburg model in the mirror symmetry. So it is important to control the strictness of R modules. But in general, if we consider just R modules, then it is not so easy to control. And for systematic study, to control the strictness of R modules, we need stronger structure, and that is twistor structure. And twistor structure was originally introduced by Simpson. So a twistor structure is just a holomorphic vector bundle on P1. And it is called pure of weight when if it is isomorphic to the direct sum of OP1n. And the twistor structure with increasing filtration is called a mixed twistor structure if the nth graded species are pure of weight n. And so we regard mixed twistor structure as a twistor structure of the vector space obtained as a fiber over 1. So to consider the space of the vector space, we consider something of P. And we can also regard twistor structure as a generalization of Hodge structure or underlying structure of Hodge structure. In the sense, a Hodge structure is equivalent to C-star equivalent twistor structure. We consider standard action of C-star on P1, and equivalent twistor structure is equivalent to Hodge structure. And he proposed a very useful guiding principle called Simpson's meta theorem, which says concepts and theorems for Hodge structures should be generalized to concepts and theorems for twistor structures. It is not always easy to achieve it, but it indicates very good direction of study. So it is very helpful guiding principle. And let me also mention some differential geometric structures are defined in terms of polar to pure twistor structure. I have not explained polarization of twistor structures. Maybe I will explain it later. But it is a kind of metric in the context of twistor structures. And it is very useful to characterize or to understand some type of differential geometric structures. For example, harmonic bundles can be reformulated in terms of polar to pure twistor structure. Actually, it is original motivation to introduce for Simpson to introduce twistor structure. Then, very roughly speaking, pure and mixed twistor D modules are enhancement of harmonic D modules by pure and mixed twistor structure. And unfortunately, it's not easy to explain the precise definitions of pure and mixed twistor D modules. So I just want to explain what kind of objects we'd like to consider. And let me remind you, the twistor structure is a structure of some vector boundaries. And to consider structure on vector space, we consider something on P1. So similarly, now we want to consider something on P1 times X as a twistor structure of a harmonic D module on X. So we regard P1 as a gluing of C lambda and C mu by the relation lambda mu equals 1. And similarly, we regard P1 times X as the gluing of C lambda times X and C mu times the conjugate of X. X dagger denotes the conjugate of X. And we consider a strict harmonic Rx module, which is an object of C lambda times X. And we also consider a strict holonomic Rx dagger module, which is an object of C mu times X dagger. And we consider an isomorphism of the restriction of these guys to the circle of lambda whose absolute values are 1. Let me remark, this guy is a family of dx modules, and this guy is a family of dx Dagger modules. So we cannot compare it directly. But there exists the equivalence between dx Dagger module and dx modules given by the duality with respect to the seek of distributions and the duality of d modules. So by using this equivalence, we can consider an isomorphism of the restriction of these guys. Then, by gluing of this Rx module and Rx Dagger module, we obtain some object of P1 times X. And so this is what we'd like to consider essentially. And actually, for some technical reasons, we use a different formulation of R triples introduced by Kurosama, which is very useful. But essentially, we'd like to consider this kind of object of P1 times X. And we would like to impose some conditions on this guy. And very heuristically, we'd like to consider the restriction of this guy to each point of x. I mean, P1 times each point of x. But in the context of D modules, the restriction to points are not so helpful. So instead, we consider the vanishing cycle functors and nearby cycle functors for any functions of this guy. And we impose the conditions to the nearby cycle functors and vanishing cycle functors. So this is one of the most important ideas of Saito. Saito introduced many important ideas and many important and original ideas in his theory of Hodge modules. And this is one of the important ideas of Saito. And then, so theory of twistor D modules was developed by Saba and myself as a twistor version of Hodge modules due to Saito based on the guiding principle Simpson beta theory. And we established an equivalence between polarizable paired twistor D modules and semi-simple algebraic canonical D modules. So sorry. Sorry, it's okay.
So if I have a family of log extents over base, you're constructing this strict polynomial module with logarithmic differential along the normal crossing divisor. Imagine that I have a family whose generic fiber doesn't have any, just a trivial divisor. So I can there over the generic fiber, I have logarithmic structure, trivial logarithmic structure. Over the special fiber, I have an actual normal crossing divisor. Does this strict polynomial module that we construct, does it in that case satisfy functoriality between generic and a special fiber?
So maybe I don't understand quite, but we have a specialization nearby cycle functor gives some specialization procedures. So I think we can use it in that.
You have a variety on it. You have a holonomic, a strict holonomic module. If your variety is smooth, you might have even a sheaf with an algebraic connection on it, so everything is okay. But then you degenerate the variety into normal crossing. There you have an actual normal crossing divisor that you can take twist the D module with that. My question is, in this degenerating family, does this holonomic strict module that you construct, does it satisfy functoriality if I pull back something from the special fiber to the generic fiber?
So maybe I don't understand, but in that case, the pullback should be considered as nearby cycle functors or vanishing cycle functors. But so sorry, maybe we need to formulate the problem more precisely. So can I discuss later?
Yeah.
Sorry. So we obtain the equivalence of paired paired twistor D modules and semi-simple algebraic canonical D modules. And as I mentioned, paired paired twistor D modules can be considered as a kind of geometric structure, differential geometric structure. So this achieves dive hop 1 in the context of algebraic canonical D modules. And dive hop 2 is also partially achieved. I mean, polarizable paired twistor D modules are preserved by the direct image via any projective morphism. And the purity is not preserved by other standard functions usually. So to achieve naive-hope 2, to achieve naive-hope 2, we have to extend the theory. We have to extend the theory, and it was done by the theory of mixed twistor D modules. So as I mentioned, there are standard functions such as push forward and direct image and inverse image and tensor and homology and duality and some others acting on the derived category of algebraic conic D modules. And we have the enhancement of these standard functions acting on the derived category of algebraic mixed twistor D modules. So this is one of the main theorems in the theory of mixed twistor D modules. For example, as a simple application, we can obtain the stoicness of the hypercohomology group of the twisted drum complex with appropriate boundary conditions, as I mentioned. And let me mention what invited us to this study. So, as well known, the cohomology group of a smooth projective complex variety has pure Hodge structures. So it has Hodge decomposition, and it also satisfies Hodge-related theorem and Hodge-Riemann binary relations. And according to Doreen, it was generalized to the existence of the mixed Hodge structure on the cohomology group of any complex algebraic variety. And it is also Doreen who established the Weil conjecture. So in particular, he established for any smooth projective variety of a finite field FQ, any eigenvalue alpha of the Frobenius action on the M-theta cohomology group satisfies the condition the absolute value of the eigenvalues is q to half of n. And by using this result, Beilinson and Beilenstein and Doreen-Gaba developed the theory of weight on power shifts on algebraic varieties over finite fields by using the Frobenius actions. And then it is very interesting to ask if there exists a counterpart of the BBDG theory in the complex algebraic geometry. According to the Riemann-Schmidt correspondence, which was explained by Andrea, power shifts are equivalent to regular harmonic D modules. So it was expected to obtain a counterpart of BBDG theory by formulating Hodge structure in the context of regular harmonic D modules appropriately. And if everything is smooth, it was done by Griffiths and Doreen by their theory of variation of Hodge structures. And in the singular, more general singular case, after the contribution of, after important contributions by many people, Moriko Saito established it, completely established it. He introduced mixed Hodge module as a mixed Hodge structure or regular harmonic D modules. And he established all the desired functoriality. But we can still ask if we can extend the theory to cover the non-regular harmonic D modules. For example, we have this kind of very simple algebraic harmonic D modules. And this is not necessary, not always regular. Well, if G has non-trivial form, it is always harmonic, non-regular. So we'd like to and so and the D module, in the theory of D modules, it is very important to consider Fourier transform. And to consider Fourier transform for this kind of very easy harmonic D modules, we'd like to generate a theory to cover non-regular harmonic D modules. And and we can also ask what can we say about naive-hope 1? I mean, for naive-hope 1, it is difficult to consider if we only consider Hodge structures. And the generalization was if everything is smooth, the appropriate generalization was done by the theory by Simpson, by his theory of harmonic bundles. And the most singular case was studied by Sava and myself, as I mentioned, and we developed twistor D modules as a twistor version of Hodge modules, and naive-hopes 1 and 2 are achieved. So actually, this is one of the end of the story. But we can ask the following question. So for some applications of Hodge theory, Hodge filtration plays very important role. So we can ask if is there something similar to Hodge filtration in the context of twistor D modules. And it was studied by irregular Hodge theories. And as I mentioned, Hodge structures are equivalent to C-star equivalent twistor structures. And between Hodge structures and twistor structures, there are other generalizations of Hodge structures. And one of the most important is an integrable twistor structure, which is a twistor structure equipped with a meromorphic connection of fold order 2 at 0 and infinity. Then we have the corresponding theory of mixed integrable twistor D modules. And there is a full subcategory of rescalable objects. And then it turned out the D module underlying rescalable object has the irregular Hodge filtration. I mean, rescalable objects are not necessarily regular singular, but they have some filtration with nice properties. And the idea of the irregular Hodge filtration was first introduced by Doreen in some special cases. And it was developed by Saba and Yu, and later improved by myself. And in the Hodge theory, as I mentioned, some numerical invariants are induced by Hodge filtrations. And irregular Hodge filtrations are expected to play a similar role. And actually, Kuresan and Saba and Yu applied irregular Hodge filtrations to study some kind of L functions. Okay. Then, so finally, I'd like to mention an attempt toward the generalization of an aspect of Hodge theories. So the key is the polarization of twistor structures. So let sigma denote the anti-holomorphic involution defined by sigma lambda equal minus lambda by inverse. Then the pullback of OP1 by sigma is naturally isomorphic to OP1. So we can consider the pullback of twistor structure by sigma. Then for any pure twistor structure of weight 0 denoted by V, a polarization of V is a symmetric product of V and sigma star V such that the induced Hermitian pairing on the space of global section is positively definite. And the weighted case can be defined by using shifting. Then a polarized pure twistor structure of weight 0 is equivalent to just a vector space with a Hermitian metric. But this concept is very useful to understand some differential geometric structures. So usually, differential geometric structures are defined by some complicated nonlinear partial differential equations. But in some cases, by using polarized pure twistor structures, we can understand the structure in a more complex analytic way. Actually, Simpson reformulated harmonic bundles in terms of polarized pure twistor structures. And before Simpson, polarized pure twistor structure of weight 0 implicitly appears in the twistor theories to describe instantons as some holomorphic data in the twistor space, which is called Penrose-Ward correspondence. So, so when we consider a differential geometric structure characterized in terms of polarized pure twistor structure, we expect it is possible to enhance algebraic operations by the differential geometric structures. A mixed twistor D modules is one example. And ADHM construction and now transform about instantons and monopoles are also such examples. I mean, they can be regarded as twistor enhancement of a kind of Fourier transforms. So Hodge theory could have, so I think Hodge theory could have a much broader scope. And so, and there should be much more equivalence and enhancement of objects and functors. And by using this idea, actually we obtained new equivalences between periodic monopoles and difference modules. which are not considered in Hodge field usually. So, so maybe it's time. So yeah, so there are. So I finished my talk by saying there are vast unexplored research areas. So I hope someone is interested in this kind of object. So thank you very much.
Thank you for the wonderful talk. Any questions?
So I meant, maybe I rephrased my question. It's actually related to the perverse sheaf of vanishing cycles that you mentioned. This twisted, strict holonomic T module, is it well behaved in terms of degeneration of a variety? If I take a variety with a divisor, then I degenerate the variety into something else, and the divisor might break into pieces. What happens to this through the degeneration family? Is it well behaved or not?
Sorry, I think it depends on the object. No, I mean, so there should be some general theory which apply it, but I don't know. So maybe we need to see. I need to know more concretely your object. I think maybe.
For instance, let's say I take P3, I degenerate it into two P3s meeting along the P2.
P3, P2.
Yeah. So now on this P3, let's say I have a strict holonomic D module, and I want to see what happens over this normal crossing variety. Again, it's related to this perverse sheaf of vanishing cycles. After taking Euler characteristic of that, it relates to invariance, nice invariance, and so on. I want to see how deformation invariant are these constructions. That's why I'm asking this. I want to see whether they deform nicely.
Sorry, what is the starting point? I mean, so
the starting point is the P3 with the sheaf. And
what sheaf?
On P3.
Any sheaf. So yeah. So maybe I think it depends on the sheaf. Yeah.
Some vector bundle of high rank on that P3 with some algebraic connection. That's it.
Yeah. So for concrete calculation, maybe I have to know what vector bundle you call. I think.
So it depends on
I think so.
More questions?
Does your theory of mixed twisted D modules have any connection to the so-called non-commutative Hodge structures?
Yes. So yeah. So maybe so it's not clear for me what is non-commutative Hodge structure. But actually, so non-commutative Hodge structure, if I remember correctly, it is given in something on C and some Hodge module on C. If I remember.
It's still some holomorphic vector bundle and P1 maybe allowing some regular singularity over the
So maybe it is close related with. Yes. Thank you very much for the good question. So I mentioned. So there is some generalization between Hodge structure and between generalization between twistor structure and Hodge structures. And non-commutative Hodge structure is one of this one, and it is very close to this one, I think.
Okay.
Yeah, and maybe some more structure is considered, for instance, Q structure or something like that, if I remember correctly.
Yeah. Okay. Thank you.
Thank you.
Any more questions?
So maybe you already mentioned this, but is this mixed twistor D module, are they a strict enhancement of mixed Hodge modules, or?
Sorry, could you repeat?
So those mixed twistor D modules, are they enhancements of mixed Hodge modules, or are they just enhancements of holonomic D modules? So what are the relations between these different things?
So this is the relation. So mixed Hodge module is full subcategory mixed integral twistor D modules. And if we forget the connection in the P1 direction, then we obtain mixed twistor D modules. So this is contained here, and there is some forgetful functor here. So this is the relation. Hodge module and twistor D modules.
But we also mentioned this naive hope one. So if you do this naive hope one for just holonomic D modules, do you get exactly mixed twistor D modules, or do you get something else?
So naive hope one is achieved for pure twistor D modules, and yeah, actually for maybe this is not answer, but this so there is a factor from forgetful factor from mixed twistor D modules and harmonic D module, but this is not essentially subjective, and the image contains semi-simple harmonic D modules. So most one is the important objects are contained in the image of this one. So yeah, so sorry, maybe this is not the answer for your question. But,
I see. Thank you.
so,
Any more questions? If there are no more questions, let's send the speaker again.